Hello everyone, and thanks for joining our talk on using AI to automate and improve game testing. My name is Konrad Tolmar, and I'm sharing this talk with my colleague Linus Gisslén. We are from SEED, research group at Electronic Arts. This work is naturally a shared effort by the SEED team, and in the end of the talk you will find contact information on how to reach us. Here's the outline of today's talk. Let's get right into it. SEED is an applied research team at EA, and our core mission is to explore the future of interactive entertainment. We basically operate in two modes to achieve this goal. First, we investigate and explore state of art by participating in the research area, by publishing and presenting papers, and working with universities. Secondly, we turn this research into prototypes, codes, and tools that could be used at EA. Next, I will briefly mention three of the core areas that we focus on before going into more details about AI for game testing. The first area is future graphics. Here we look into how to make our games shine with cinematic quality. But we're also developing tools that simplify and speed up content production of all the assets that are needed in modern video games. Here's one example of that work, hybrid ray tracing that was done together with NVIDIA and the Pika Pika project that was presented here at GTC. You can check it out at the SEED websites providing in the end of the talk. The second area of research for SEED is advanced avatars. As we all know, games are fundamentally about creating visually conceiving avatars. They should look good, behave naturally, and be well fitted into the environment. Here it's also important to understand how avatars are designed and implemented into the games. This will create tools that help with both quality as well as quantity. The last area is deep testing. That is a focus of today's talk. I leave it now the word to Linus to continue the presentation.
So, hello everyone. I'm Linus Gisslén. As previously mentioned, I'm a senior research engineer and team lead for something we call deep testing. Deep testing is a bit of play of words on deep learning and in-depth testing. So I'm here today to talk a little about in detail of some of our projects that we are working on. So first, to set the scene a bit, and for those who are familiar with games and testing of games, so why do we even test games? So in this talk, I'm focusing on kind of logical glitches, like for example, the player gets stuck, that you have missing collision boxes, causing the players to walk through walls, players falling through the ground, or imbalances in the games or in characters, but also visual bugs and load tests, for example, where you have to test map garbage. And you can see some visualization to the right of the examples. So first, to motivate why we are looking for automated compared to human play testing, because you can also test games by using humans. So for automated play testing, one of the main benefits is faster testing, which means it's much shorter time to market. We also get less chip bug if we can test more in breadth. Also, we will have less exponential growth in cost of testing when the environment grows, like now with this new trend to have an open world games. Becomes more and more assets to test, and that grows exponential. Also, it leads to much less manual and mundane labor, leaving more time for meaningful testing for the human play testers, which means we will have happy employees, but also it would reduce risk because mundane tasks are usually prone to errors. So the goal with our research is in short to research human-like automated game testing, because we want to test as closely as how players perceive our games. To do that, we use our machine learning to accelerate testing both at scale and breadth. And as I said, the goal is to free human resources from repetitive tasks to do more meaningful work when it comes to testing, like testing the game, like how fun it is to play, for example, is very important to us. So the research we are developing, is to find the bugs faster, but also to improve the overall quality, but also to do this in real time. And this also, of course, can lead to a more interesting game AI. If we can get gameplay testing bots, we can also get interesting game AI out of that, we believe. So first I want to talk a little bit about visual testing. And it's exactly what sound is the testing of the visual content. So first, again, to set the scene, what leads to graphical issues, and it's a lot actually. You have all the components like art pipeline, production pipeline, the asset database, the rendering pipeline. If something goes wrong at any point, you're going to have problems with the visual. But also, especially now when we have cross-platform, some things might look good on our PC where we develop, but then shipped on PlayStation, something might get wrong because you are missing some drivers or whatever it could be. So if we find bugs in the visual content, it's basically an aggregation of everything that can go wrong, and it's a lot of things that can go wrong. So just to give you examples of showing how common this is. So this is a Jira ticket search for one of our games, and it leads to more than 20,000 graphical issues found by human playtesters. And the majority of these is displayed here. Is either you have a replacement or a missing texture, and it is as it sounds, the texture has gone missing. Maybe it's didn't load from the database, or maybe it never existed even. Also, you have stretched textures and low resolution textures. And also it's basically what it sounds like. There's something wrong with the texture. It's on the object or the asset, but it's something wrong with it, stretched or low resolution. So in order to train this, we have two ways of getting trained data. So either we can take the training data by looking at Jira tickets, for example, to gather in-game graphical issues. So that's actually real data you can train on. But the problem with that is that we have a lot fewer examples. Even though 20,000 examples sounds like a lot, it's not really good enough to train a neural network to identify those. We have very little control over data. For example, in the example that I showed, many of them put red boxes around the examples, and that's going to lead just the model is going to try to search for red boxes, and that's of course not going to exist. So that's also something that is important. Also, it's really hard and slow to create the data set because you have to do it by hand. And also, there's a big risk of biased data sets. So, for example, you might have vast majorities for one bug, and then the model will not be good at finding the other kind of bugs. So the other option is to generate data. And the advantage with that is that you have control over the data. You have the control of the object, the lighting, the rotation in the background. So you can augment your data very easy. And with automated gathering, you can easily get more than 100,000 samples in a few minutes. Also, this can also be generated by the assets in the game and in the same game engine, which means that even though it's not real data, the data is going to look very similar to real data. That's one of the big advantages. And also we can balance the data so we know that it's not going to try to learn to just look for one bug, but all of them. So with these insights, we set out to create our synthetic data, and here are 4 different environments that we looked into. One is like a natural-looking environment, looking like more or less trying to mimic how real world looks like. the second line here you see stylized futuristic data samples. And the third or fourth are kind of combination. And third is handmade objects in an environment that is set out to be a little bit without background. And fourth is handmade object in the natural environment. So you have a lot of shadows, a lot of occlusion and so on. So the model, the approach we took was looking at the kind of three different approaches, either unsupervised learning, anomaly detection, and supervised learning. And when it comes to unsupervised learning, it's really good for seeing previously unseen errors, and it's ideal, but it was very hard to train and not really practical, because then I had to learn to be able to detect itself and what is, you know, anomaly in the game and what is not. The same with the anomaly detection. It's really good to find outliers, but and it's then really good to find something that is completely unexpected, but we don't really have that. We kind of know or expect what kind of graphical issues we're gonna get. So this made it also not practical, because it was also really hard to train. So we went for the supervised learning, and of these three different subsets, so to speak, is object detection. We didn't find any real benefit of that, because we can control the camera, so we know where the objects are. Segmentation was interesting, so you can point out in which part of the image you had your graphical issue. And it was very computational costly, and it worked, but benefit was very small, because usually when you present this image to a game dev, they see immediately where in the image it's wrong, where it's wrong, so it didn't add any value really. So the classification of the full image was the cheapest and the most effective we found to do this. So out of 200-300 different architecture for image recognition, we picked 5 because we didn't want to try to handpick them too much, because that would also bias our model to our training data. So we selected 5 and compared those. And out of that, we decided to use something called ShuffleNet V2, which is a good combination of a fairly small network, but it was really good at classification rate also. And some specs, we used one machine with a dual GeForce GTX 1080, and resulting in a training time of less than 10 hours. And also, as the network wasn't that big, we could also run this in real time when we did inference. And if you want to read more, you can see our paper called Using Deep Convolutional Neural Networks to Detect Render Glitches in Video Games. And some a little bit on the results. So here you can see the model is really good at finding placeholder and missing textures. But it wasn't that good at finding low resolution texture, which is also a little bit expected, because we also saw that in the Jira database, that even human playtesters, they mistake normal textures as low resolution textures. So it's actually wasn't a bug, but it thought it was that. So it is also hard for humans to a little bit assess if it's a low resolution texture or if it's supposed to be like this. But it shows very promising results on finding kind of very visual bugs like missing and placeovers. And that's also really good, because these models are really good at detecting what also human players sees easily, which means that they can pick out the most obvious errors in the image and leave those that are not really visible anyway to human players. So here's a video a little bit on the results and the idea that we would like to use this. So to the left, there's an input from something called a smoke test, where we have a camera going around in the environment, and usually a human sits and watch these and see if there's something wrong. But now we feed it into a network. And to the right, you see the output, and the red line shows the classification. If it shows a 1, means it sees a glitch. and 0 it means it doesn't see a glitch. And the blue line is the confidence score, and that's supposed to be as high as possible all the time, of course. And with that, we can also help it to reduce false positives. So the idea with this is also that you should not only see this as a tool to use in real time, but also you can have this as a overnight runs where you can get statistics the day after, how much of the environment that the model sees problems, and that could give an indicator if there's something wrong with your build. And also this can be integrated into the game engine fairly easy. So, and if you have a low confidence score on your model, you might request another image, so you can rotate the camera or change the lighting to get another, and then you can get a better confidence score and improving your results that way. So next I want to talk a little bit about gameplay testing, and here we are mainly looking in using reinforcement learning. So I want to start off again here by motivating why we use reinforcement learning in gameplay testing. So the nice thing with RL is that it can learn to exploit games without being, or even learn to play games without even being told. And that also leads that it can learn to exploit games. And that's very nicely visualized here to the right. This is an experiment from OpenAI where they took an old Amiga or Atari game, I forgot which one, called Coastal Guard, and they used RL to play this. And after a while, the agent found an exploit in the game, meaning that it instead of playing the game as it's supposed to do, it goes a little bit off track and picks up these green boxes, which then respawns, and then it can pick it up again, and then it gets a lot of score, which is a bug in the game, and it hasn't really been found in these 30 years it's been around. But it's very nice that the RL agent could find out without being told to do that. And the OpenAI sees this as a little bit of a problem with RL, that it doesn't play as intended, but for us it's perfect. If we can use RL to be able to not only play the game, but also if there's something that to exploit, we can learn to exploit that, because that's just what we would like to find before the player does. And also other things that is nice with RL is it can learn things. So it doesn't have to be scripted to do something. You give it a reward function to play the game, and it will eventually learn to play the game by testing stuff. Also, it allows us to test games without having to script, and this is really useful for not everyone at EA can script. It's we have a lot of other kind of talent, and scripting is maybe not something that everyone knows. So if you want to have other people who can program to test games, could be a really nice way of introducing them. Also meaning that we don't have to script, we don't have to rewrite scripts, but instead we rewrite. So if we change something in the environment, we just need to retrain, and that's much cheaper compared to having to rewrite every time you do something, because then you have to bring in a human every time. So, and also this means that you have scale, but also speed, so you can play hundreds of games simultaneously, making testing coverage much better than traditional methods. So, but we have some challenges definitely when it comes to RL, and these are the things that we try to address. So the main part is generalization. And this is very important, and I'm going to talk a little bit about that in the next few slides, but it's important for the RL agent to be able to generalize over new environment. And that meaning that, because in testing you often change the map or environment a lot, you change characters and so on. So we need to be able to fairly good generalize over different games or environments. Also, something that's very important is interpretation. So for example, in the previous game we drove a boat, it just learned to exploit the game, but it will not tell you, of course, that it done that. It will just try to pick it up and then it play the game as it thinks it should be played, maximizing its score. So you have to look at other metrics. So, and in this example, you could have looked at the score, seeing that this is unreasonable high, it shouldn't be this high, and it could be an indicator. But also, for example, if you have agent that learns to exploit the game by walking through a wall where you're not supposed to do that, you can use visualization to do that. And these are things that we also think about how we can interpret the behavior of the RL agent. Also, another thing that is very important is to have control, but also human-like behaviors. And this is also important because we want to test the games in all the variety that human players play. So, for example, if you have more aggressive player, more passive, more curious players, and more explorative players, we would like to cover all that. And also, it's very costly to retrain our agent, so we would like to be able to fine-tune behaviors. So if it learns to navigate, we would like maybe to change a little bit in some other behavior, but we don't want to retrain the whole model. And this is then fine-tuning of that. And also something that it's very common, or like very a feature amongst humans is that have very different skill levels, so we would like to train for that as well, so we can also cover the whole spectrum of skill as well. So a little bit about generalization. So the problem with RL agent on this is that if you train on a fixed map, which you often do, it leaves that it memorizes the map, meaning that if it sees a new environment, it cannot really generalize. So then we need to retrain. And the video here shows an example of that. So they play it very well until they come to a place where they haven't really seen this before, and then they kind of confidently fail by jumping off the edge, more or less. And this is due that it trained on an environment that looks similar in the beginning, and then this environment turns, and they have no idea what to do there, so they just continue because they memorized this is how I'm supposed to run. So the use cases for us are a little bit obvious. So, for example, testing and playing of previous unseen maps, which happens a lot because that's what we do in game development. We change a lot on the environment. But also, it's interesting for real-time applications where there's no time to retrain. So, for example, human-created assets. If people want to create their own cars or their own environments, like buildings or similar like that, we would like to be able to test them. But also for guided content generation. So if we would like to have this in real time, we're not going to have time to retrain, but we would like to have an agent that can handle a big spectrum of different challenges. So to continue on this, there are some solutions. So one solution was presented last year by Riese et al. And that is to use procedural content generation, meaning that the environment is constantly changing. It's generated by rules, so it's all the time updating. So the agents are forced to learn new behavior and confront new situations. PCG is of course no guarantee for good training environment because you don't know if it's going to be challenging, but also you don't really know if it's going to be an impossible map. So we have in our research, we looked at a solution to this, and that's another RL agent that creates the environment, and that's going to learn the agent itself to not make impossible maps, because if you have a feedback loop from the solver, it's going to learn to not create impossible maps. And I'm going to present this a little bit here in the next slide. So first, the statement here, the environments needs to be neither impossible or trivial to be able to train a good RL agent, but also needs to be diverse so it becomes robust to novel situations. And also we would like to have control of the generation, which is then a bonus because then we have an agent that can produce new environments for you, and that can help you with designing new maps, for example. So our approach is has been taken a generator and a solver approach, meaning that you have a solver, the normal RL agent, but also you have a generator, which then is an RL agent which generates the map for you. And connecting these two together ensures that the generator will learn not to make impossible maps, but also not trivial. And if we add an auxiliary input, we will also have control of the generation, and also the auxiliary input can also further diverse the environment. And I'm going to explain this here. So first, we take a normal reinforcement learning environment where we have a solver which plays the game that controls its action in the environment, and the environment sends back an observation and reward. And then you add a generator on this and connect that to the environment. So it generates the map in sequence. So it can, for example, generation for a racing game would be the banking, the turning, the distance, how long the segment is. And you get reward both from the environment. For example, environment could give a negative tick at each time step to further hasten the generator to make a quick map, for example, but also from the solver. And if the generator goal is to make something difficult, it can get a positive reward if the solver fails, but also at the same time, if you want to make an easy map, you can get a reward if the solver solves the map. And by adding an auxiliary input to switch these values, you can learn to make both, and that gives it also a more diverse environment where it learns to make easier and hard maps. So to show some results on this, I have a video here. And this shows the generator making the blocks and the solver is trying to solve, and their common goal is to get to checkerboard. And we switch the auxiliary input. The auxiliary input -1 means difficult, and +1 means easy. And you see that's changing up in the middle of the screen, and here you can see it. So here we start with auxiliary input of 1, meaning easy. The blocks becomes big, and the jumps long or shorter. And then when the auxiliary input decreases, it makes the map more difficult, but also doesn't make it impossible, because the solver is also learning at the same time. So if it becomes impossible, the solver will stop. It will not try to make the jump, and the generator will not get any reward for that. And it's really good for generation, but also it makes the solver more robust to changes in the environment. You can see here to the right you have the RLPCG agent, and to the left it's trained with traditional ways, where it's trained on a fixed map. And this is an unseen environment where it's made by a human, so they haven't played this before. This is the first time. We can do similar, but using kind of a driver's game. The generator is making the road, and also you can see here different auxiliary inputs, where now it's supposed to make it the most hardest. It makes it a lot of turning, a lot of banking, so the solver drives off the road, but also doesn't make it impossible, to encourage the solver to actually try and fail sometimes, so it gets its reward. And when we move the goal, it will just recreate a new map, so we can have a constant creation of new environments. And here's another tricky one, and then we're gonna switch back the auxiliary input to make it easy again. And now we'll create something that's simple, so it makes just a track towards the goal. And the vision we have with this is that if we can have agent that can play a fairly large amount of different environments, we can have this as a real-time player also. We don't have to retrain. This is an example of that, where a human is building a track and the agent is playing that at the same time. So you can see here that it stopped when it couldn't make the jump, but also it tries to make the jump, and then you can see like which kind of jumps are impossible and which are harder and which are very easy. Especially if you add a full population, then you can see that some actually fail, and you can adjust the difficulty, and you can get statistics how many actually make the full map to get an idea how difficult the map is. And we have a paper on this called Adversarial Reinforcement Learning for Procedural Content Generation, if you're interested in learning more. And with that, I'm handing over to Conrad again to talk about curiosity.
Thank you, Linus. Next, we will talk about how to empower the RL agents with more human-like behavior, and in this case, curiosity. What we learned in previous work was that the RL agents is useful for game testing and improved testing compared to scripted bots. But it could still be improved further. Here is the core idea to optimize playtesting. The agents is therefore encouraged to be curious about the game, and we want to test if this helps us maximizing exploration and coverage. For this reason, we started by creating a larger sandbox to test these ideas. Here in the video, you will find different problems that was designed into the environment, such as exploits, missing collision detection, and areas where it's easy to get stuck. You can also see some other game elements like elevators that the agents can use to get around in the world. Last, we can now also see the scale of the agent compared to the elements in the game. So here is our proposal. Implement novelty-seeking or reinforcement learning by adding a curiosity personality to our new agent. Our approach is actually fairly simple. We reward the reinforcement learning agents based on the novelty of the experience that they are collecting. We keep track of the position and the events that the agents have already seen or triggered, and we reward them for moving towards previously unexplored locations. However, regardless of how good this agent might become, they are not going to tell us if something is wrong with the game. It's our job to ensure that sufficient data and proper metrics are collected while training is taking place. The evaluation and analysis of this data is what actually will enable us to identify potential problem or design oversights. Here, a total of 320 agents are trained in parallel. On the video to the right, we can compare the performance of our agents against a random policy. The blue dot represents positions around the map that the agents managed to reach. To the left, we have some information about the time it took to collect this data. Our agents quickly learned how to navigate most of the map, and we were able to reach around 90% coverage in less a day of a training. Over here, we have another example of coverage around one of the navigation challenges. As shown to the left, the blue path represents trajectories that an agent would have to follow to reach the top. RL agents are capable of solving navigation challenges like this one, while simple heuristic or random actions are very unlikely to solve this in a reasonable amount of time. Another interesting thing we can do is to create some sort of connectivity graph based on the trajectories followed by the agents. Here we have a small segment of this directional graph showing us how different positions visited by the agents are connected to each other. We can then make use of this graph and standard path planning algorithm to show the game designer and the developer how the agents manage to move between any 2 points in the game. That's reaching into the end of our presentation. So let's sum up what we have talked about so far. Basically speaking, we argue that AI and ML is well used for game testing. For example, simple techniques like convolutional neural networks is useful for detection of glitches. More powerful machine learning techniques like reinforcement learning can also be used to operate agents for game testing. And here it's the unpredictability of AI could somewhat become a strength than a weakness. We now, however, to develop more human-like behaviors like curiosity and similar. We are also working with on ways to use reinforcement learning in more dynamic environment. Last, the agents will not tell you where they have been yet. So in order to understand the RL agent's gameplay, we need to develop new ways to visualize the gameplay so game designers and developers can understand and use these tools. Finally, here are some future challenges that we have somewhat touched upon in the talk. Let me pin down the two first ones. That's all about bringing research into application. To start with, the tools that been presented here needs to be integrated into the game development pipeline, and then in particular into the QA process around game testing. This is not only about tech, but it's also about practice and guidelines. For example, how would you design a game that is more ready for ML testing? Secondly, scaling is a fundamental challenge in machine learning, and also here. Taking glitch detection as an example, how could you design and provision a platform that could consume hundreds of hours of gameplay every day? And then not only one game, but many games, as well as cross-platform on PCs, different form of consoles, and many mobile platforms. That concludes our talk. Thanks for listening. Here you find some contact information and a link to the SEED homepage. Now it's time for questions.